Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
So what is an interrupt? Let's take an example to understand the meaning of an interrupt. Suppose we are studying in our room and suddenly our mother knocked the door and she told us that please do some work for me. Okay, like go to the market and bring some things for me. Okay, so she wants that we should stop studying whatever we are doing at that time and then first listen to her and then go to the market, bring the household things for her and then again resume our studies. So that is a kind of interruption, because whatever work we are doing at that time, suppose we are studying in our room or we are doing something in our room, that work we have to stop. We have to first listen to our mom and do the work for her, and then again we are doing the same work what we were doing earlier. Now, in the case of microcontrollers and microprocessor, interrupts is like that some peripheral devices, if they want to communicate with the microcontroller or the microprocessor, they interrupt the processor. Okay, so at the time of that interruption, what the microprocessor or the microcontroller is doing, it finishes that work. Means suppose it is executing some instruction or doing some operations, it will first finish that work, then it will acknowledge that interrupt. Like for every interrupt we have some programs, some instructions, like interrupt service routine is written. So it is going to execute that interrupt service routine and again it is going to come back to the main program that it was executing at the time of interruption. So that is called an interrupt. In simple language we can say that disturbance. Okay, so that disturbance which is caused by some peripheral device, that is called an interrupt in the case of microprocessors and microcontrollers. Okay. So we can say that during the program execution, when the microcontroller is executing the program, in the program we have various instructions. So microcontroller was executing some instruction. Okay, so during the program execution, if some peripheral device it want to transfer the data or it want to receive that data, or we can say that if it wants the service of the microcontroller, then it is going to generate an interrupt and then it will get the service from the microcontroller, because microcontroller is doing some work, and if some other device wants its service, it has to first generate an interrupt. It is going to send a request, and when that request is accepted by the microcontroller, then microcontroller will give its service to that peripheral device. Now, when the microcontroller is interrupted, means the interrupt signal is generated by the peripheral device, that interrupt signal will be given to the microcontroller. So, microcontroller, it is going to jump at a memory location where the interrupt service routine is written. Service routines, we say about it, it is a type of subroutines. So, subroutines are what? They are short programs which are written at some different memory location other than the main main program. Okay, so microcontroller is executing the main program. When that interrupt signal is given to the microcontroller, it is going to jump at the memory location where the program called interrupt service routine is written. It is going to execute that interrupt service routine, and when that interrupt service routine is completely executed, at the end of the service routine, return instruction is written. So that return instruction will cause the microcontroller to return back to the main program what it was executing earlier. Okay. So after execution of that interrupt service routine, the processor, the microcontroller, it is going to return back to the main program and resume the execution of the remaining instructions. So that is the behavior of the microcontroller whenever it receives an interrupt signal, and how a peripheral device it generates an interrupt signal. So this was a little bit introduction of how the interrupts work. Okay, now let us come to the steps which are taken by the processor or the microcontroller when an interrupt signal is given to it. Okay. So let's have a look about all the steps which are taken by the processor while processing an interrupt. The first step is that whatever instruction the microcontroller is executing at that time, it will first complete the execution of that current instruction. Now when the instructions are executed, the instructions, they have an instruction cycle, means the time taken to complete the execution of an instruction. Suppose in that instruction cycle we have various machine cycles and various T states. So when the microprocessor or the microcontroller, it is interrupted, let's suppose if it is at the second machine cycle, but it has to complete the execution, it is taking 4 machine cycles to complete the execution of that current instruction, but at the time of second machine cycle it is interrupted. Okay, so it is going to first complete the execution of that instruction, then only it will go to the next step. So first step is to complete the execution of the current instruction. Now when the microcontroller it is interrupted, it has to jump to the memory location where the interrupt service routine is written. Now when it comes back after the execution of the service routine, it has to resume the execution of the remaining instruction, means the main program, it has to return back to the main program. So we know that in the microprocessors and microcontroller, the address of the memory location where the next instruction to be executed is written, that is stored in the program counter. Okay, and the flag register, or we can say the program status word register, it stores the status of all the flags like carry flag, auxiliary carry flag, and parity flag, overflow flag. So the status of all these flags is stored in the flag register or the program status word register. So the contents of both the program status word, that is the flag register, and the program counter, it holds the address of the memory location where the next instruction is written. Okay, so the contents of program counter along with the program status word, they are stored in the stack. Stack is a temporary, it is a memory location, okay, which is used for temporary storage of data. Okay, so that temporary data, that means the program status word and the program counter, their contents is stored in the stack. So second step is to store these contents in the stack. So to store the contents in the stack, we have the instruction push. Okay, so here I have written that the program status word that is pushed to the stack. Pushed means the contents of the program status word flag register, it is stored in the stack. Next step is to the program counter, that means the register which is holding the address of the memory location where the next instruction is written, so that when the microcontroller returns back, it knows the memory location, the address of the memory location from where it has to resume the execution. So program counter content, it is pushed to the stack, that is also stored in the stack. Next step is to interrupt flag is reset. In microcontroller, we have a flag which which tells about the status of the interrupts. So because the microcontroller, it has jumped to the, because it has acknowledged that interrupt which was given to it by the peripheral device, so that interrupt flag has to be reset again, so that another interrupt can be given to the microcontroller. And next step is to program counter, it is loaded with the interrupt service routine address. Because now the microcontroller, it has to jump to that memory location where service routine is written, so program counter, it is loaded with the address of the service routine, so that microcontroller can go to that memory location and start the execution of service routine. So if we diagrammatically represent this whole procedure, then suppose this is our microcontroller and it is the peripheral device. Now this peripheral device, it has given an interrupt to the microcontroller. Suppose microcontroller, it is executing our main program. This is the main program. Suppose this is this second instruction written in the main program. So it is going to first complete the execution of this second instruction. Suppose it is move A, R2. Okay, so the execution of this instruction will be completed. Then the contents of the program counter and the program status word, they will be stored in the stack. Stack will be a memory location. Okay, in this memory location, first the program status word and then the program counter. Suppose this instruction move A, R2, it is written as 8000 memory location. Next memory location is 8001, so that will be the contents of the program counter. So 8001 will be stored in the program counter. Now from after the execution of this instruction, the microcontroller, it is going to jump at the memory location where interrupt service routine is written. Now all the instruction in this service routine, they will be executed. In the last, we will have the return instruction. So when this return instruction is executed, microcontroller, it is going to jump back to this memory location. It is going to get the contents from the stack again. That means it is going to pop the contents. Storage is done by using the push instruction, and getting out, retrieving the contents, it is done by using the pop instruction. So using the pop instruction, it will get the contents of program counter and program status word, and then it will resume the execution of the remaining instructions of the main program. So this is how an interrupt is serviced by the microcontroller, and these are the steps which are taken by the controller whenever an interrupt is given to it. So last step will be ISR. Okay, so these are the total steps which are taken. First step was it is going to complete the execution of the current instruction, then program status word is pushed to the stack, then program counter content is pushed to the stack. After that, interrupt flag is reset, program counter is loaded with the interrupt service routine address, it is going to jump at that. In the interrupt service routine, it always ends with the return instruction. So when this return instruction is executed, it is going to pop the current stack top to the program counter and then the current stack top to the program status word. So diagrammatically, we have represented all the steps that how the microcontroller, it is going to process the interrupt request which is given to it by a peripheral device. Now let's come to the classification of interrupts in 8051 microcontroller. The 8051 microcontroller, it is the most popular and most popular, and most of the time it is used, commonly used general purpose microcontroller. So here we are studying all the interrupts which are related with the 8051 microcontroller. So let's come to the classification of the interrupts. So first classification of interrupts is external and internal interrupts. External interrupts are those interrupts which are generated through the external pins of the microcontroller. Means peripheral devices, they are going to give the interrupt request at the external pins of the microcontroller. Whereas the internal interrupts, they are generated internally in the microcontroller. So external and internal interrupts are those, like external interrupts are those which are initiated by the peripheral devices through the external pins of the microcontroller. Like in 8051 microcontroller, it is we have different pins. So on those pins, the peripheral devices, they are going to send the interrupt request. In 8051, we have two external interrupts, external interrupt 0 and external interrupt 1. Okay, so these interrupts are initiated by the peripheral devices through the external pins of the microcontroller, whereas internal interrupts are those which are activated by the internal peripherals of the microcontroller, like the timers and serial input output ports. So those internal peripherals, if they are sending some interrupt request, then those interrupts will be called the internal interrupts. Like in 8051, we have one serial interrupt also and two timer interrupts. So these timers and serial input output, they are the internal circuitry of the microcontroller. So if any internal peripheral is generating an interrupt request, that will be called an internal interrupt, and if any external device is generating the interrupt request, then it will be called an external interrupt. So that is the first classification of interrupts in 8051. Second classification is maskable and non-maskable interrupts. Now suppose Suppose in microcontroller 2 or 3 interrupt requests, they are simultaneously given. Okay, suppose microcontroller it is getting 2 or 3 interrupt requests at the same time. So at that time, how many which interrupt request will be executed first, which will be executed at second, or which will be masked or disabled, or which will be first acknowledged. So we have, on the basis of that, we have two types of interrupts. Maskable interrupts are those interrupts which can be disabled by the microcontroller using some instructions or some commands. So those interrupts that can be masked or disabled, they are called maskable interrupts, and those interrupts which cannot be disabled or masked are called the non-maskable interrupts. Maskable interrupts are those which can be disabled by the processor using the program, whereas non-maskable interrupts are those which cannot be disabled by the programmer using the program. Okay. Now, third classification is based on, is called the vectored and non-vectored interrupts. And this classification is based on the address of the service routine. If the address of the service routine it is fixed for that interrupt, it will be called a vectored interrupt. Okay, because the address of the service routine is fixed for that interrupt. Whereas if the address is provided by some peripheral device, those types of interrupts are called the non-vectored interrupts. So we have vectored and non-vectored interrupts. So the starting address of the service routine, it is called the vector address. So for vectored interrupts, the starting address, that is the vector address, it is fixed. Whereas in the non-vectored interrupts, the starting address, it is provided by the peripherals. Now, how the peripherals, they provide the vector address of the, or the address, starting address of the service routine. First, the peripheral device, it will send request to the microcontroller. In response to this request, microcontroller, it is going to send an acknowledgement signal. Acknowledgement signal indicates that this request has been received by the microcontroller. So microcontroller sends an acknowledgement signal to the peripheral device, and this acknowledgement signal is INTA. So this when this INTA is given to the peripheral device is going to send the interrupt vector address to the microcontroller. Okay, so this is how the address is provided by the peripheral device to the microcontroller. So these type in which the address is provided by peripheral device, those types of interrupts are called the non-vectored interrupts. Whereas the vectored interrupts, the starting address is predefined. There is no need to give the address of that separately. Okay. So this is the classification of interrupts in the 8051 microcontroller. Now let's study the types of interrupts of 8051, that how many interrupts are available in 8051 microcontroller. In 8051 we have 5 interrupts. Some of these interrupts are the external interrupts and some of them are internal interrupts. So out of these 5 interrupts, we have 2 interrupts are 2 are external and 3 are internal interrupts. Okay, and all these 5 interrupts, they are maskable and vectored. So if we are asked that out of the classification of the interrupts, what is the nature of the interrupts of 8051, we can say that it has total 5 interrupts. Out of those 5 interrupts, we have 2 interrupts which are external interrupts and 3 interrupts which are internal interrupts, and all the 5 interrupts, they are maskable and vectored. Means we can disable all the interrupts also, and vectored means all the interrupts, they have fixed, they have predefined starting address of vector address. So let's see that what are these 5 interrupts. So these are the 5 interrupts of the 8051. First we have external interrupt 0, timer 0 interrupt, external interrupt 1, timer 1 interrupt, and serial interrupt. So out of these 5 interrupts, we have 2 external interrupts, that is external interrupt 0 and external interrupt 1, and we have 3 internal interrupts, that is timer 0 interrupt, timer 1 interrupt, and serial interrupt. Because these interrupts, they are generated by the internal peripherals like the timers and the serials. In 8051 we have 2 timers, timer 0 and timer 1. So both those timers, 2 timers, they can generate the interrupt also. So for them we have timer 0 interrupt and timer 1 interrupt. Now all these interrupts, they are maskable and vectored interrupt. So vectored interrupt means their interrupt vector address is predefined. So these are the vector addresses. Vector addresses means for every interrupt we have a service routine. So that service routine is written at some memory location, and microcontroller has to execute that service routine. So the addresses of that service routine is fixed. For external interrupt 0 we have 0003. For timer 0 interrupt we have 000B. External interrupt 1 we have 0013. Timer 1 interrupt 001B, and serial interrupt is at 0023. So these are the addresses of the memory location where the service routine is written. Now when these interrupts are masked, we have some priorities that if suppose all the interrupts are given at the same time to the microcontroller, so which will be executed first and which will be executed at the last position. So out of these 5 interrupts, the external interrupt 0, it is having the highest priority, and the serial interrupt, it is having the lowest priority. Okay, so this is how in this order the priority decreases. External interrupt 0 is having the highest priority and serial interrupt is having the lowest priority. Okay, so this was about the 5 interrupts of the 8051. Other than these 5 interrupts, we have 2 registers in 8051. These 2 registers are used for the all the processing of the interrupts in 8051. Like we have 2 interrupts, that is interrupt enable and interrupt priority. These 2 registers, that is IE and IP, these are used for enabling or disabling the interrupts or to decide the priority among the interrupts. So 8051, it makes use of 2 registers to deal with the interrupts. These two registers are IE and IP. IE is interrupt enable register and IP is the interrupt priority register. Both these registers are 8-bit registers. So the 8 bits of these registers, they are defined some functions. So let us study the format of the 8 bits of both these registers. First we will start with the IE, that is interrupt enable register. So these are the 8 bits from D7, D6, D5. 8 bits of the interrupt enable register. Now this register, it is used to enable or disable the interrupts, means to mask or unmask the registers. If the bits of this register, they are 1, means if any of the bit is 1, it means that that particular interrupt will be enabled, okay, and if any of this is 0, it is going to disable that interrupt, okay. So 1 means it is going to enable and 0 means it is going to disable. Now first bit, that is D7 bit, most significant bit EA, it is to disable all interrupts. So EA means enable all interrupts or disable all interrupts. So its value means it can be 1 or it can be 0. So depending upon its value, all the interrupts, all the 5 interrupts, they will be enabled or disabled insignificant of the condition of these bits. Suppose like if this bit is this bit is used to enable or disable all the interrupts. So when EA is equals to 0, okay, means this bit is reset, then no interrupt will be acknowledged, means all the interrupts will be disabled because 0 is for disabled. So if this bit is 0, it means all the 5 interrupts, they will be disabled. No interrupt is going to be acknowledged by the microcontroller. And if this bit is 1, means interrupt is enabled or disabled by the individual bits, means then the enabling and disabling will depend upon the status of these 5 bits. Now ES is to enable the serial interrupt, ET1 is to enable the interrupt which is for timer 1 overflow. This is for the external interrupt 1, this is for timer 0 interrupt, and this is for external interrupt 0. So these are for the 5 interrupts of the 8051, and this bit is for all the interrupts. Okay, so this IE interrupt enable register, it is used for enabling or disabling all the interrupts or one of the interrupts of the microcontrollers. These 5 can be used to enable, disable the individual interrupts. Like suppose ES is 1, so ES means that serial interrupt, that will be enabled. If it is 0, that will be disabled. ET1 means timer 1 interrupt will, if it is 1, then it will be enabled. If it is 0, then it will be disabled. So this is for the individual interrupts, and this bit is for all the interrupts. Now next register we have is the interrupt priority register. This register is also an 8-bit register, and it is used for setting the priority of the 5 interrupts. Now this interrupt priority register, its 8 bits are defined like this. These 3 bits are not defined, they will be used for future interrupts. Okay, now we have 5 interrupts in 8051, that is serial interrupt, timer interrupt 0, timer interrupt 1, and external interrupt 0 and 1. So PX0, it is for deciding the priority of the external interrupt 0. This is for deciding the priority for the interrupt for timer 0. This is for external interrupt 1. This is for timer 1 interrupt, and this is for serial interrupt. So P is for priority, and X0, T0, X1, T1 and S, these are for the interrupts. Now if these bits are 0, suppose any of the bit is 0, then that corresponding interrupt will have a lower priority, and if any of the bit is 1, then that corresponding interrupt will have the higher priority. Suppose that PS, the status of all this is, suppose PS is 0, 0, 0, 1, 0. Okay, so all the interrupts will have lower priority, PT0 will have the higher priority. So 0 will decide the lowest priority of the interrupts, and 1, if any of the bit is 1, that will give that interrupt the highest priority. So in this way, this IP register, it is used for setting the priority among the 5 interrupts of the 8051. So these two registers, that is the interrupt enable register and the interrupt priority registers, they are the special function registers in 8051 which is used to deal with the interrupts in 8051. Okay, so in this video we studied that what is an interrupt, how the interrupts are classified, what are the steps which are taken by the microcontroller whenever an interrupt is given to it by the peripheral devices. Then we studied that what are the types of interrupts in 8051. We studied that we have 5 interrupts in 8051 microcontroller. Then we studied the 2 registers IP and IE which are used to deal with the interrupt structure in 8051. So I hope that this topic, that is interrupts in 8051 microcontroller, it is clear to you. Thank you.